get it? Okay. So we are essentially finished with the part of the course that will be covered in the midterm. So today we are starting after the midterm. So everything till last Friday will be in the midterm. From today on, it won't be. It will be in your final. Okay. So you have homework that is related to last week. So please do the homework. That will be due on Friday as well. And that homework will get you prepared for the exam. All right? So if you have done the homeworks, the 4 homeworks, you should be, if you've done it yourself, you should be well prepared for the exam. Okay? And if you pay attention to what is going on in class, you've done all the homework yourself, especially the warm-up problems, if you've done it yourself, then you should have really understood the basic concepts that is required. Okay? So, but if you have talked to each other and got help and so on, then you're on your own. I can't help you there. Okay? So that's that. So what we have done so far? What we have done so far is basically look at the way we characterize materials. And that we characterize materials by the features of the materials themselves. And the features of the materials that we look at are the atomic structure, the bonding, and the crystallography. And from the atomic structure and the bonding, we develop various spectroscopic methods. And from the crystallography, we develop diffraction methods. So that's what we've done. And there is one more major way of characterization of materials, and that is imaging. And I haven't found yet, I'm still struggling, a way to sort of introduce imaging just like I've introduced spectroscopy and diffraction. It does come from the microstructure, but I'm not able to write a whole chapter where I use the imaging and then introduce the concepts of imaging. But imaging in many ways is really a way of collecting the same sort of information in a spatially resolved fashion. That is, you collect spectroscopic imaging using a fine probe as a function of position, and then you plot particular intensities as a function of position. And therefore, you can create images. And this intensity could also be contrast. It could also be, so in a way, the imaging sort of follows from these 2 methods that we already have. So we will talk about imaging perhaps in a week or 2 weeks, when we will start introducing the 2 important imaging techniques that we have, which is scanning electron microscopy and transmission electron microscopy. And then we will probably finish the course with scanning probe microscopy. So that is what we will do in the end. We'll do the 3 imaging techniques at the end of the course. So before we get there, what we have to now do is to take a small detour, in the sense we have to now say, okay, we have done these techniques. Now we have to look at the various probes that constitute these techniques. And the probes that we use are, basically we have already introduced most of them. That is, we introduce light, which is photons. We use electrons. Photons also includes X-rays. We use neutrons. And we also use ions. Okay, and the probes are generated using different sources. And the question then is, what are these sources, and what are the characteristics of these sources that we use to that when we develop these probes? And so we are going to look at these probes first, how we generate the probes, what are the characteristics of these probes, and then the probes, when they interact with materials, there is a certain nature of that interaction with the materials, and part of that interaction with the materials, if you don't know what you're doing, then you can actually cause damage to the material that you're trying to look at. So you have to also understand what is the nature of the probe, how it interacts with the materials, and what sort of damages it causes. And then for this particular chapter, because I couldn't find any other way of bringing it in, is since we are going to talk about ions as a probe, we're going to also discuss a number of ion-based methods. And 2 important methods that are used based on ions Rutherford backscattering spectroscopy, which is sort of a diffraction-like event, but we are looking at the energy of the ions that come back. So that is called Rutherford backscattering spectroscopy. And the second spectroscopy is called secondary ion mass spectroscopy. And that is called SIMS, or RBS is the first one, and the second one is the secondary ion mass spectroscopy. So what you do in that case, you go and have an ion that is incident on the sample, it ejects secondary ions, and then you measure the mass of the secondary ions. And the mass is done by so-called mass spectrometers that measure the mass of the ions that come out. And so we are going to talk about different techniques where we are now going to talk about various probes first. We are going to talk about what they do to the material. First, how the probes are generated, what are the characteristics of these probes, how they interact with the material. Then we're going to talk about ions, and then we're going to spend a substantial portion, at least one lecture or a lecture and a half, on ion-based methods. Okay, that's where we are going. But before we do, I want to ask you once again, is there anybody in class who doesn't understand reciprocal lattice? The way we have introduced reciprocal lattice, it's really, really important that you understand the concept of reciprocal lattice and how it's a very simple concept, but of great consequence in all the characterization, especially the diffraction methods that we keep talking about. Anybody here who does not understand the reciprocal lattice? Good. So now we can move on with the probes. So the first important probe that we always talk about is light. Right? So we use light, and we have talked about light in different contexts. Light meaning we are using light across the entire spectrum, electromagnetic spectrum. We often, when we mean light, we only imagine visible light. But while light extends in the ultraviolet, far into the ultraviolet, it also extends far into the infrared. And so various light sources produce light across the visible spectrum and extending perhaps into the infrared at higher wavelengths, or extending into the ultraviolet. So I'm not going to spend too much time, but you should have a general sense of the various light sources that we have. And here in the next slide, it sort of shows you the various sources and the sort of the spectral attributes of the various sources. So here is the wavelength, and here are the spectral intensity. I've highlighted the region, the visible spectrum here, roughly from 400 to 700 nanometers. And the important sources that you have, the original sort of source that was used was basically you took a tungsten filament and you heated it. You passed current and you heated it, and as you raised the temperature, it produced light. Do you know what is the basic physics of this? Black body radiation. So the higher the temperature, the higher it emits light, and so the tungsten was the first source that was used because it was a refractory metal with a high melting point. These are important points you should remember. Why do people use tungsten? Because it's a refractory metal, it has a high melting point, and you can raise it to high temperature to get reasonably intense black body radiation. If you took something at a low melting point, you can't get its temperature high enough if the emission is not so intense. So tungsten was used as the first source, and a derivative of that is the so-called tungsten halogen lamp. So that's the one. It functions in the same fashion, except there is some halogen in the vacuum tube, and then you produce it. So the important characteristics of the tungsten halogen lamp is that if you look across the wavelength, it sort of increases, and then over here it flattens out. But there is not much variation. It's rather smooth variation in the emission as a function of wavelength. That's the one, and the important thing to recognize for this one is that it produces a continuous spectrum. Okay. Now, the second way that people produce light was to take two metal rods, pass a current through them, and then generate an arc between these two metal sharp tips of this metal rod. So these are the so-called arc lamps. And these arc lamps, as you can see, we have these different mercury lamps, metal halide, and the xenon lamps. Initially, people created the arc lamp, and then what they had was they had various gases in there, and once these arc was struck, the halogen, the gases got ionized, and they produced their own spectrum. And therefore, depending on which gas you put in there, the spectrum looks different for these arc lamps. So there are three different lamps that are shown here. One is the mercury arc lamp, where you can see this is the continuous line here that is shown here. Its features sort of almost die out at the end of the visible spectrum. And about 1/3 of this is in the ultraviolet, and 1/3 of it is here, and the other 1/3 is sort of lost in the mercury lamp. Okay? Then you have these xenon lamp, which is very, very interesting. It has a flat profile. It has a flat profile across the visible. And then most of it, a good half of it, is in the infrared. Okay? This flat profile finds particular use in biology. And the reason is that they use various species or ions or materials that fluoresce. And if you want to fluoresce, if you have a sharp line, and if the fluorescence is off the sharp line, you can't get it to fluoresce. Whereas here, because it's a continuous one, you will always find some part of the incident radiation that will create the fluorescence. You don't have to be exactly one. And the other one is the halide, the mercury halide lamp, which is also shown here, which is this long dash. And this mercury halide lamp has some very interesting features in the visible. And the important feature is this one at 546. Does anybody know what color this is? Yes, green. It's this yellowish, slightly yellowish green. And this line is used often as a standard. And why is it used as a standard? Do you know? Does anybody know why green is important? Green is really important. Okay, you're raising my hand. So.
No, sorry.
Yes?
It's easy on your eyes.
Excellent. Your eyes, the peak sensitivity of your eye is in the green. So anything that is, so if you go to an electron microscope and you look at the screen of the electron microscope, it has a green phosphor. The reason it has a green phosphor is that is the peak sensitivity of your eye. And therefore, green is an important color for all of us. Okay? So that's where we have the maximum sensitivity in terms of your detection. So this line is very important because it's often used to calibrate various spectrometers. Okay? So there is nothing more in terms of this, how light is generated. So there are different ways of generating light. You have to know the spectral features of various sources, and you have to just pick one that really suits your particular needs. And of course, cost also becomes a factor, and so you should pick. Typically, people use either a mercury lamp, arc lamp, or a tungsten halogen. The xenon lamps are used if you really are interested here in the infrared. And if you want a flat spectrum here, also you can use xenon. If you're using experiments that use biological fluorophores, then you use that because you don't have to hit it exactly. You always have some intensity to excite them. And so you can choose them depending on your needs, and you can pick them according to the money that you have. It always comes down to that. Finally, it really comes down to what you can buy for the money that you have, and you have to figure out what is the optimal thing that you can buy, which will do as much of what you want to do without compromising anything else. Now, in addition to this, there are also lasers that are used, right? And I don't know how many of you know a little bit about how lasing works.
Somebody's talking about LEDs.
Okay, I will skip it then. I mean, I just didn't want to spend a lot of, that's why I didn't send you a slide. If Peter had covered it, then it's fine. Okay, so then the other sources that we use, so that's photons. The second one that is of importance is electrons, right? So electrons are also produced in a similar way. They're produced by two different methods. The source for electrons is produced by, does anybody know what the two different methods are? I have already mentioned it before. How about somebody from this side of the class? Or is people speaking from here? How about somebody from here? What are the two different ways of producing electrons?
You can create them by tunneling them across.
Yeah. So the way that's called a field emission method. And then there is another method, which is thermionic. You just heat it. Okay. So you heat it, and then and the way that you approach it from the physics point of view is to look at the work function. And so if you want to move the electrons out, you have to produce sufficient energy to overcome the work function. And the way you overcome the work function is by heating. That is the simple way, and it's called thermionic emission. So if you look at that, so that is the next slide here. And this I have already discussed before. So you have a periodic potential. When you come to the boundary of the crystal, that periodic potential changes. You have a break in symmetry, and when the break in symmetry takes place, you have essentially this work function that you have to overcome. Okay? And that work function that you have to overcome, so that is the Fermi level EF and the vacuum level EV. The difference between the two is the work function. And if you heat the crystal, then you can overcome the work function and you can get the electrons out. Another way to do the same thing is apply a potential, a very strong potential, and change that potential barrier. And if you put a no field, the potential barrier looks like that. If you put a weak field, the potential barrier bends. And if you put a very strong field, then the potential barrier comes all the way down and the electrons can tunnel through. Or with a little bit of heat, electrons can go over that barrier and you can get so there are two ways. So this is purely thermionic emission. If you're using a purely tunneling physics, it's called a field emission, and it's often referred to as a cold field emission. You can combine the field emission with a little bit of heat, then it is field emission combined with heat. Those are often, many commercial TEMs have that combination. Even though they call it a field emission, they call it it is actually a thermal combined with a field emission. And they have different names, but let's skip it. But most of the commercial ones are not cold. So what would be in your mind the difference in the electrons that come out from this and from this? What would be the significant difference? Does anybody have a guess?
The energy they come out with?
That's right, the energy spread. The energy spread, the energy width of this would be larger than this. And the colder the source, the narrower the energy spread. Okay? So here it would be the broad energy spread. Here the energy spread would be narrow. If you combine this with a little bit of thermal emission, the energy spread will go out a little bit. So if you have a cold field emission, the energy spread will be very narrow. So that is the trade-off. Okay? There is another trade-off that you do, and that is the current that comes out. Okay? The amount, so in all of these sources, so let me write a couple of things, the important criteria that you need. So one is called the energy spread. So that is the energy spread of the electrons and the energy that they have. If you're doing spectroscopies with the electrons, the narrower the spread, the better the energy resolution of the spectra that you collect. The second one is the current, the total current. That is the amount of the total electrons that come out from the source. But often we are not interested only in the total current. We are interested in something called the current you know that what is the difference? The difference is when we have an electron microscope or an electron probe, we want to focus the beam. And when we focus the beam, we want to see what is the total current per unit area that we can produce. Because the signal that will come out will depend on the current density. Right? Yes, please.
Oh, sorry, no.
Oh, you're just stretching.
Yeah, sorry.
Okay, fine. So this is the current density. So these are the factors when we look at electron sources, we'll be looking at the energy spread, we'll be looking at the total current, and we'll be looking at the current density.
So are people building like a liquid helium field emission, or is
the original cold emissions were all low temperatures.
Okay.
But obviously in a commercial instrument, that is not the issue.
Yeah.
And I will show you a table where you will see the differences between these machines. Now, the important thing is that the current that comes out, the current density that comes out, let me just write an equation. So this is for the thermionic emission. For the thermionic emission, the current density that comes out is proportional to the square of the temperature and exponentially dependent on the work function. The higher the work function, the lower the emission. So what you want is you want to find a low work function material so that you can get a higher current density. The typical material, one of the lowest work function materials, does anybody know what is the lowest work function material? The lowest.
Oh, lowest.
The lowest work function materials is cesium. It is an alkali metal. Yeah. So cesium, unfortunately, is pretty unstable. So you can't use that as a source. So you go to the next one that has a low work function, which is tungsten. So actually, if you had a choice, you would use cesium. But you don't, because it's unstable, so you use tungsten. Right? Now you use tungsten, and actually it turns out that there is another material which is a binary. which is even has a lower work function than tungsten. And so often, if you go to an electron microscope, the old electron microscopes had a tungsten filament. Nowadays, they have lanthanum hexaboride. So the lanthanum hexaboride has a much lower work function than tungsten. Yes, please.
Do you have the numbers of those?
Huh?
Do you have the numbers of the work functions? And
I will show you a table just now. So all this will be there. You talk.
Okay.
Yes.
Can you remind me what TC in that equation is?
You tell me. Now you're the one who always asks questions that I can turn back. What would TC be? What would TC be? You're talking about thermal emission, huh?
The initials of total current?
No. We look, just think about it a little bit. We are looking at thermal emission. You have to do something to. You're going to heat it up, right? You're going to heat up, right? So what is the current? As you raise the temperature, the emission will go up. And here the emission goes up as the square of the temperature. The Tc stands for the temperature of the cathode.
So, okay, I believe you, but then what is the T in that denominator? Is that also the temperature of the cathode?
Yes.
Oh.
So they're the same thing?
Yes.
Okay. That's right. Okay.
But this is general expression for the temperature in terms of the. All right, that's a good question. I'm glad you keep asking these questions. I can turn them back and ask them back to you.
We've got time. It's wild.
You're just asking the right question, so.
Okay, cool.
Because I would have asked the same question, you asked them, so I can turn them back. Okay. And there is a similar expression for the field emission. I'm not going to do it here. When I send you the chapter, it's there. The discussion is there. I just use the equation, and you can see it depends on temperature and number of other factors. But this is what you should know. Well, you should know this part. Yeah.
So since modern TEMs use a conjunction of field emission and thermionic, is it safe to say that while the field emission causes a narrower energy spread, that the thermionic emissions probably lead to higher current density, which is why we use both?
Yeah. That's it. Basically what you're doing is we are lowering the barrier effectively, and we're still getting the thermionic emission. So we are putting the field emission to lower the barrier, and we still get the thermionic emission. So what you do is you get a higher current density, but you get a larger spread as well. So when I show you the table, which is coming next, you will see we can compare these different sources. Yeah.
Is there a way to focus the spread down after it's all been emitted, or do
You mean the energy spread?
yeah, where you just let the
Yeah, that's a wonderful question. Yes, you can. What will you lose if you do that?
You would lose intensity.
That's exactly right. So basically what you have a big energy spread. You will use some sort of spectrometer to cut down the energy spread. You just take what is coming through, some sort of filter that filters energy. You lose intensity. So if you can afford to lose intensity, then you can, that's what you do. So you guys are all thinking in the right direction. That's great. Okay, so then let me now show you the table. So here's the table that puts all the important factors. From when you start to look for a source, when you want to look for the electron sources. So here, Helena, right?
Yeah.
Yeah. So there's your work function, the first line. Tungsten is 4.5. The lanthanum hexaboride is 2.7. For the field emission, of course, it's the same, 4.5. It's tungsten.
Does the field emission, work function matter to a significant degree? Because it's always.
Well, you have to still reduce it from some point down to some point. You still have to apply enough field to reduce it. But if you're starting at 20, you have to apply a much larger field.
Okay.
Yes.
Why not lanthanum hexaboride in a field emission?
It doesn't work. It's an insulator. It's a real different material.
Oh,
It's a different material.
so it can't tunnel.
Yeah. So it's a good question, but it doesn't work. I would have asked the same question back to you, but anyway, you have to move this thing forward. So forget about that is that constant, forget about that. Then working temperature. So that's the important thing. So thermionic emission, you operate the filament at a very high temperature, 2800. Lanthanum hexaboride is operated at lower temperature. And then of course this field emission, this is the combined one. You heat it to a certain point, you get an emission, and then you operate at a lower temperature than the original. And of course there's the vacuum required. That's actually an important factor because we are doing cold emission, we need higher vacuum. So you have all the costs start to go up because you have to go from a typically 10-7 torr to much 2 orders of magnitude higher vacuum. Then of course the whole thing becomes much more expensive. Then the lifetime, of course the filament lifetime is also an important thing. When you heat it up to such high temperatures, the filament doesn't last very long. So in the old days, 40, 50 years ago, 40 years, 30 years ago, when people were working with microscopes, you would be always taking out the gun and changing the filament every week at least. Now you don't do that. Then the total current. Now the total current is the important thing. So on a thermionic source, this number should be 10 to 100, and that's 1 to 10. So you can see what you're doing is that in a field emission source, the source is very small, and so the total current that you produce is quite small. Whereas the thermionic emission produces a lot of current. The source is big. The area of the source is a little bit big. But the big advantage of that is that current density in a field emission is huge orders of difference from. So the total current is small, but the current density is high. And the current density is high because all the electrons are coming from a very small area. Now the current density has both an advantage as well as a disadvantage. If you have advantages that you can pump a lot of current electrons into a small volume, the disadvantage is that you can pump a lot of electrons into this small volume. The reason is, in electron microscopes, you use very thin samples. When you focus the electron beam onto a very thin sample, if you're not careful, you start drilling holes in the sample. Especially with the field emission gun, when they introduced the first field emission gun commercially, people were not familiar with this. They would focus the probe and they would just see a hole. You get a little bit of intensity, whatever you're looking for, and after a few seconds, you'll be getting no intensity. You're wondering what's going on. Essentially, the sample is gone. There's been a hole drilled in there. Yeah. So that is the real, you have to be careful because you're putting a lot of current in there. So current density. And then there is the angular, then the energy width. This is the important thing for every spectrometry that you do. If you're looking at the energy width, it's about 1 to 2 eV for the thermionic source. For the lanthanum hexaboride, it becomes a little bit better because you're operating at lower temperatures. Here, the lowest one is cold emission. This is for the thermally activated field emission. So you can see the energy difference. So if you're looking for spectrometry, electron energy loss spectrometry, you can get much higher resolution in the spectrometry. So remember we talked about X-ray absorption, the fine structure. You can get the same thing with the electron energy loss spectroscopy. And that fine structure there will depend because your spectrum that you see is convoluted by the energy spread of the gun. And therefore, if you have a bigger spread in the gun, your spectrum is going to be broadened out because whatever you're seeing is going to be convoluted with the energy spread of the gun. Okay? And then the brightness and the diameter that you can get. So you can see these characteristics in this table is included in your both in your handout. I will, if I get 3 volunteers at some point, I will actually send out this chapter as well. Any questions about the source, the electron source? Okay, so now how does a gun work? So a typical gun works like this. So you have a cathode shown at the top over there. I can't reach up there, so it's right there, the one that looks like that. And it has it's heated, the current passes through that UC, the potential, there's a current that's passing through the gun. The gun is, so it can be, it can be either a thermionic emission or a field emission, and that produces electrons. Electrons are going in all directions. So you want to bring the electrons back to focus. So you have a kind of a cylindrical, what's called a V-naught with a small hole. And that V-naught, it's actually a cylinder, it shows like, but it's a cylinder with a small hole. And that's kept at a negative potential. So what happens is that the electrons are coming out and they are repelled by this V-naught and they are all focused to this point. And that crossover point has a certain diameter and becomes what is called a virtual source of the electrons. So the electrons originally coming from the cathode, but this diameter, now the electrons, that is your virtual source. Those electrons are then accelerated by this anode. So when they say your electron microscopes operate at 100 kilovolts, it is this potential U0 that is 100. It is not the UW. That's inherent, that you, only if you are interested in the details would you find out. That's typically of the order of 5 kV or something. But these are, that is just to produce the electrons and focus the electrons. And this 100 or 200 or 300, the acceleration voltage of your microscope is determined by this U0. That is, then the electrons from this crossover are accelerated by this potential, and they cheat it or they trick the electrons by creating a small hole. So as they accelerate, they just come to the hole. Okay, and that is what produces this, and then the electrons come out with a certain angular spread. Everybody clear on how an electron gun works in terms of the microscope? So if you go to an electron microscope, you have to, in the old days, you had to keep taking out this V-naught and changing the filament and making sure the filament is centered on the hole of the V-naught, the cup. If it's not centered, obviously that will be distorted and that will produce real poor performance. So you have to make sure it's centered, and then you put it in there, align it, and then you put it back. And then this is the important thing to recognize, is that UW is just the V-naught potential, which is a small one. When people talk about a 100 kilovolt microscope or a 200 kilovolt microscope, it's this potential of the anode. Okay? The potential of the anode, which is U0, which is what they are always talking about. You have a question? Something looks like it's not clear.
I'm just a little confused why there's so many batteries in different places.
Well, just different potentials are applied at different places, and you're just showing you what those different potentials are.
Oh, so it's like to scale. If there's one and the other one's like double.
Just, no, it's not to scale. It's just to show you, it just yeah, to some extent. Yeah, but it just shows you see UW, U0. Yes, these are, in some ways, U0 will be 100, 200. UW maybe.
But in like the actual device, do you have 3 different batteries in?
Well, it may or may not be a battery, maybe just a source. Maybe you could take your you could take the current that we have from the line and then step down, or transformers or whatever. It's just a current source.
Okay.
Yeah. Yes.
Can we control that alpha by moving the crossovers?
You can control. There are a number of ways of controlling alpha. It's true. I mean, by crossover or making the hole smaller, the aperture size, or you can actually put subsequent apertures here that will control the alpha. So that's called a condensed aperture. So you can put in these apertures here afterwards to control the alpha.
Isn't it done with a magnetic beam? Isn't it done with like a magnetic beam?
The focusing is done with a magnetic lens, but what he's asking is, how do we control the alpha? You use apertures, and apertures can control what comes out, what angles. But the focusing is done with the lens, and the lens is a magnetic lens. Yes, any questions? I'm sorry, a lot of this would be so much simpler if we just go to a microscope and see it, but it's very difficult for a large class to go and see these things. Yeah.
So jumping off of Amy's question, basically because this is the electronic gun, you would have the magnetic coils after basically.
Well, there would be number of coils.
Yeah.
There'll be one set of coils which are called the condenser lenses, then there are the objective lenses, and then there are projective lenses, and so on. So the main imaging workhorse of this, like any other microscope, is an objective lens.
Yeah.
We'll talk about microscopy in a little bit. We'll talk about microscopy too. We'll talk about optical microscopes after this chapter. So then we will, and essentially you do the same thing. All right. So that's the gun. Any questions on this? So the other sources, now we have electrons, we've talked about photons, we've talked about electrons, then the next sources are neutrons. Obviously these are not laboratory sources, so for the neutrons, you go to a specific facility. And there are two ways neutrons are produced. Does anybody know what are the two ways that neutrons are produced?
One is with a proton beam. You do I think it's a beryllium source, and you knock neutrons loose.
Mm-hmm. So there are two ways. One is fission. When you have a radioactive element that decays, it produces neutrons. So that used to be the traditional way of producing neutrons. What you're talking about today, what you're talking about is what is called a spallation source. They're not so common. There's only one user special spallation source in the US, and that is at Oak Ridge National Lab, or whatever it's called, ORN. It's in Tennessee. That's where you have a spallation source. Basically, you hit some sort of a metal target. It can be beryllium, it can be also mercury. You just hit it with high energy protons, and when they hit it, it gives out neutrons, and then you can take the neutrons and then you can collimate it using some sort of a crystal and produce only a certain wavelength coming through by diffraction of those neutrons by this.
There's one in Los Alamos as well.
Yeah, but that's not a real user facility. That's just a household thing. They really use it. Whereas the one in Oak Ridge is a real user facility. You can put in a proposal and use. Even students can do that. Mm-hmm. So that's a nice thing about the Oak Ridge one. Now there are two important things from a fundamental physics point that you should know. That is, important thing is about the mass of these particles. Okay, the mass of the electron compared to the mass of the proton and the mass of the neutron. The mass of the proton and the mass of the neutron is much bigger than the mass of the electron. Right? So a good number to remember is 1,000. Right? It's roughly 1,000 times heavier than an electron. Now, if you have energy, if you're accelerating these particles by a certain energy, that becomes its kinetic energy. And if you divide it by the mass, that will give you the velocity squared. So the velocity or the wavelength will depend on the energy divided by the mass. So the wavelength will be different for the same energy because the mass is 1,000 times higher. Now, if you take ions, now you have a complete atom with just one electron removed. Then its mass is even higher. It's 10 to the power of 5 times, roughly. That's a good number to remember compared to the electron. 10 to the power of roughly 3 for the protons and 10 to the power of roughly 3 for the neutrons. So it's not 10 to the power of 3, but that's a number, so roughly 10 to the power of 5 is a good number to remember. So ions are much heavier than electrons. So the wavelength and their behavior is very different. The other thing that you should intuitively remember is electrons, protons, and ions have charge. Neutrons don't have charge. So the electrons, the protons, and the ions can interact with the electron shell, whereas the neutrons are purely going to be affected by the nucleus. So the characteristics of the scattering of the neutrons is quite different from the characteristics of the scattering of all these charged particles. Because the charged particles have Coulombic interaction with the electrons, whereas the neutrons have no Coulombic interaction because they are neutral particles. This is very important. This is the difference you will see between these. Yeah.
And also because of that, that means we can't really like use an electric field or anything to filter out or accelerate neutrons. So how do we make sure we have a narrow span?
Well, I can ask the question back to you again. So how would you do it? It's your turn now.
Would that just mean we have to be very consistent with how we excite them?
So they have a certain wavelength, and you can choose wavelength by another method.
Like the Gaussian curves.
Yes.
Wouldn't that severely reduce the intensity to all?
It's possible, but you produce so much in the installation, so you can afford to lose. So what you do is you put a diffraction grating or a crystal, diffractant crystal. It's basically that's what you do, and then you select the wavelength. So Michelle is happy. She got even. So that's good. Okay. So that's that part. Yes.
But can't a neutron physically hit an electron and
It'll
doesn't?
be very small.
Okay.
The cross section for that is small. We'll talk about cross sections in a bit.
Okay.
Yeah. Physically, that would be very small. Okay. So we have any questions about this? I'm going rather slow, but that's okay. Because just so that you understand the concepts of these various probes. It's important to understand this. Let me do one more thing before the class ends. Okay. So we're going to talk a little bit about deflections of charged particles, and we have already seen this before, so I'm going to just do a slide quickly. We can deflect charged particles either with electric fields or we can deflect them with magnetic fields. So the first one is to deflect it with an electric field. This part, you have an electric field, you have a charged particle, and then as the charged particle goes through, it's going to be deflected by the electric field. And the angle of deflection, we can easily show, maybe I give this as a homework problem, and so also it can be deflected by the magnetic field. And this is the Lorentz force, QV cross B. We've already discussed this. Now the important thing that you should remember is that the angle of this deflection does not depend on the charge or the mass of the electron. Okay, there's a little derivation that shows you this. On the other hand, here the angle of deflection depends on the magnetic flux. So if you are using, and it also depends on the mass and the charge. So if you're using ions, because ions have a large mass, right? If you want to focus them with the magnetic field, it will be very, very high fields that you're going to. Please, two hands going up. Yeah, go ahead.
It's really hard to see that equation.
It is in your, it will be in your notes. Which is hard to see?
The magnetic one.
Okay.
Yeah.
Okay, now?
Now it's really small.
Well, I can't please you, can I? I'll try my best. How about that?
That's good.
A little bit further.
Alternatively, there is a projector screen.
Well, I don't know how to please you, but I'll try. Keep trying.
There is a projector screen too.
I know, but if I keep lowering and raising the screen, I will just be wasting a lot of my time. But let me just do it for this. Let me do it at the end. I will do it in the next class. You will also have this.
Okay.
Okay. So, so
if A, you're passing it between two charged states, and then B, you're passing it in the middle to